Historically, cognitive neuroscience has operated on a divide-and-conquer approach, mapping specific cognitive functions to isolated anatomical regions of the brain. While this modular methodology provides structural insights, it fails to explain the dynamic, continuous integration of multisensory information that characterizes actual human experience. Attempting to capture this holistic activity through physical fMRI scanning is hindered by significant logistical friction, exorbitant financial costs, and the physical constraints of the hardware itself. These physical limitations have historically restricted neuroscience to an observational science, creating a bottleneck that prevents us from predicting complex cognitive behavior at scale. The development of multimodal foundation models, specifically Meta's Trimodal Brain Encoder version 2, or TribeV2, is shifting the discipline toward a predictive, computationally driven field. The architecture is built on the thesis that the high-dimensional semantic spaces of deep neural networks mathematically align with the representational strategies employed by the biological primate brain. This alignment enables in silico neuroscience, where foundation models act as digital twins. Researchers can utilize these models to run thousands of virtual experiments without the need for human subjects or physical scanners. TribeV2 provides a mathematical link between artificial neural network computations and raw biological human experience. The TribeV2 pipeline begins by ingesting environmental stimuli through 3 pre-trained, structurally frozen foundation models, acting as specialized feature extractors. On the top track, textual data is processed by Llama 3.2. To capture retrospective memory and context, the architecture prepends the preceding 1,024 words to every target word being analyzed. The middle track uses VJEPA2 Giant for visual processing. This model analyzes dense 64-frame segments over 4-second windows to encode the nonlinear spatio-temporal dynamics of video media. On the bottom track, auditory and acoustic information is extracted utilizing the WAV-to-VEC-BERT 2.0 foundation model. These 3 distinct semantic representations are then mathematically resampled to a standardized 2 Hz temporal grid. This synchronization translates multisensory inputs into a unified mathematical sequence for the neural backbone. Moving to the center of the pipeline, the 3 representations are concatenated into a unified time series with a model dimension of 1152. This data enters an 8-layer transformer backbone designed to synthesize information across a continuous 100-second window. This expansive temporal horizon is a deliberate biological design choice. It is used to implicitly model the hemodynamic response function, or HRF. In human physiology, the HRF dictates that blood flow to active neural tissues occurs with a delayed latency of 4 to 10 seconds following a neural event. The transformer is not merely organizing data, it is algorithmically accounting for the physiological constraints of the human cardiovascular system. On the right, the temporal output enters a subject block. To match the constraints of physical scanning protocols, the high-frequency outputs are decimated to 1 Hz. This output is projected onto a 3D mesh, mapping anticipated neural activity across 70,000 distinct voxels, including both high-resolution cortical vertices and deeply embedded subcortical centers. Because the architecture was trained on a massive, unified dataset of over 700 subjects, it has abstracted the universal principles of neural response, enabling zero-shot generalization. The model functions as an advanced filter, stripping away the mechanical and biological noise, such as respiratory interference and pulse artifacts that typically plague raw neuroimaging data. Consequently, the AI's generated canonical brain response is now frequently more representative of average human cognition than any single physical fMRI recording. This predictive capacity has immediate utility in sectors like quantitative finance, where global markets are driven by collective human psychology and biophysics. The left column here shows the flaw in traditional trading systems. They rely on rigid syntactic classification, which often fails to capture the emotional nuances and time-sensitive fluctuations of human traders. In the right column, brain-encoded sentiment models identify shifts in neural processing. They can detect when high volatility causes the brain to bypass analytical logic in favor of associative, fear-driven rule processes. By running global economic discourse through a biological predictive model, trading systems can anticipate the impending shift toward fear-associated circuits. This allows algorithms to adjust portfolio exposure before these predicted affective states manifest as market-wide panic. Quantitative finance is evolving from reading economic news to mathematically anticipating the biological reaction that news will trigger in the human nervous system. A primary limitation of Tribe v2 is its deterministic nature. Without active external stimulus, such as silence, the model generates a static, flat prediction. This contradicts biology. The living brain exhibits spontaneous fluctuations even at rest. Future foundations must evolve into generative, oscillating state space models capable of simulating these autonomous neural rhythms. We also face a spatio-temporal gap. fMRI provides millimeter spatial accuracy but slow temporal data, while EEG provides sub-millisecond temporal data but poor spatial localization. Synthesizing these disparate data types requires omnifunctional models. These utilize a sparse mixture of experts' routing architecture to train simultaneously across heterogeneous signals without one modality degrading the performance of the others. Fully integrating these frameworks will yield a master predictive model, possessing both absolute spatial precision and sub-millisecond temporal fidelity. As predictive models scale alongside unregulated consumer neurosensors, the historical privacy boundary of the human skull is becoming increasingly compromised. This introduces the threat of algorithmic cognitive hacking, where predictive tools are optimized to manipulate choices by targeting subcortical neural pathways without a user's conscious awareness. These risks necessitate the establishment of neurorights, a legal framework being drafted by international oversight entities and early legislative precedents like Colorado's HB 24-1058. The cornerstone of this framework is cognitive liberty, the absolute human right to self-determination over one's brain chemistry, and protection from coercive algorithmic surveillance. As AI achieves biological resonance, protecting human agency requires enforcing strict meta-alignment governance before the internal landscape of human thought is fully accessible to algorithmic monitoring.